growth in braided categories.
Okay, thank you very much. Sorry that I'm not with you guys there. So my talk is on my joint work with Dave Pennies, which is uploaded in December of last year. And it's dedicated to the following, one may say, technical problem. So for many years, experts in tensor categories and related areas have struggled with problems where it's needed to show that a certain tensor category, usually braided tensor category, is rigid. In many problems, one can establish weaker versions of rigidity, such as Grothendieck-Verdier, or weakly rigid, or the like. But then to show you that the category is actually rigid in the strong sense is a lot of work. This has been the case in actually Finkelberry's work on proving Kazhdan-Lustig equivalence for positive integral level. Then there was actually an error in his paper, which was corrected later by using some powerful technology from algebraic geometry, namely the Linde formula. And then there is work of Huang, who also gave another way to correct it, but also using a lot of hard work with vertex operator algebras. And there was a conjecture in the book of Bakalov and Kirillov that a modular functor always comes from a modular category that also was hinged upon this type of question, which remained open. And this paper is dedicated to settling these questions and giving a technique how actually to do this with minimal effort. There is still some open problems, but I think in all the known cases when this has been a difficulty, we were able to deal. So let me start. So I'm going to work over a field K. There is going to be a field K, and C is going to be a Cauchy complete K-linear braided monoidal category. So this means it's closed under taking direct sums and direct summons. And it has finite dimensional morphism spaces, and the morphisms of the unit object equals K. And so I want to make the following definition. So suppose X is an indecomposable object in this category, then we will say that X is non-negligible if there exists a Y in the same category such that the unit is contained as a direct summand in Y tensor X. And it's clear that we can choose Y indecomposable. So then we also say that X is of moderate growth if there exists N such that dimension of the endomorphism algebra of X to the N is less than N factorial. This is a little bit different from traditional definitions of moderate growth, but not much. Actually, it's a weaker condition. And the main theorem that we prove with Dave is that every non-negligible object X of moderate growth in the category C is rigid. Non-negligibility is a very weak version of rigidity. Actually, it's not strictly weaker. It's kind of, none of them implies the other. But let's say in a semi-simple category, it's a weaker version of rigidity. So this Y would be like a weak dual of X. And if it exists for every object, if it exists for an object X, then actually it must be rigid. And the only real condition here, which is not usually imposed, is moderate growth. So let me explain. So this is a very turns out to be, it's not very difficult to prove this theorem. I think the reason it wasn't proved before is that people didn't think of using moderate growth condition, which is crucial for this theorem. And luckily, in most applications, this moderate growth comes for free. Let me discuss, so I will first discuss implications of this theorem, then I will discuss the proof, then I will discuss some counterexamples showing that conditions cannot be removed, and then I will discuss some more applications. So let's say that C is of moderate growth if all indecomposable objects in C have moderate growth. And the corollary of the main theorem says that if C has moderate growth, then every non-negligible object in C is rigid. And so this can be applied to R categories, which is a special case of Grothendieck-Verdier categories. So there is a definition which can be found in a paper of Boyarchenko and Drinfeld, but actually even earlier in works of Barr. So an R category is a monoidal category C, such that for every so it doesn't even have to be linear, but the condition is that for every object X in C, the functor Z maps to home from Z tensor X to 1 is representable by some object denoted X star. Well, this will have to be a functor because by Yoneda lemma, the assignment from X to X star, some contravariant functor, from C to the opposite category of C. The condition is that this functor should be an equivalence. So that's a special case of Grothendieck-Verdier categories, as I said, in which case it's more general and one is replaced by a dualizing object K. And such categories are also called star autonomous. And this was, they appeared in the work of Barr a long time ago. But for semi-simple categories, this is equivalent to the notion of weak rigidity. So in that case, this, it's equivalent to notion of weak rigidity of Bakalov and Kirillov book, that for every simple object X, there exists a simple object X star, such that one is a direct summand in X tensor X star. And this is equivalent to requiring that the Grothendieck ring of C is a based fusion ring. So it has duality at the level of Grothendieck rings. And the corollary of the main theorem is that every semi-simple braided R category of moderate growth is rigid. And more generally, this holds in a braided ring category of moderate growth if every object is a quotient of a direct sum of tensor products of non-negligible objects. So ring category means that it has right exact tensor product, not necessarily semi-simple. So this already is nice because this simplifies some results of Huang, who has to work very hard to prove rigidity of representation categories of strongly rational vertex operator algebras. A corollary of this is that resolution of this long-standing problem in the Bakalov and Kirillov book, which says that if C is a split semi-simple category, just a category, then a modular functor based on C, as in the book of Bakalov and Kirillov, is the same thing as a modular fusion category structure on C. So this was known up to this equivalence between weakly rigid and rigid, but in this case, the category is finite. Well, maybe I should say finite here. And okay, so this kind of takes care of this, and this is actually quite useful. For example, recently using this fact, Pierre got far, and of course using some other powerful techniques such as Simpson's non-abelian Hodge correspondence, he proved that braid group representations attached to braided fusion categories over complex numbers are completely reduced. And the same is true for mapping class group representations. It's a very interesting result. Now, let me discuss some application to semi-simplification. So assume that K is an algebraically closed field. Then if I have a rigid object, X, then we have a notion of trace in X. So this is so you can take trace of endomorphism of X. Well, of course, in braided categories, you cannot take trace from X of a map from X to X, but you can take only trace of maps from X to X double dual in tensor categories. But there is a canonical map from X to X double dual, which is let's say Drinfeld isomorphism, and it's defined even without the ribbon structure, even though it won't be a tensor morphism. And then one can show that X is non-negligible if and only if this trace is not zero. So direct sums of negligible objects form a thick tensor ideal. And then we can define the green ring K of C, which is the green ring of the quotient C mod I, with Z bases formed by isomorphism classes of non-negligibles, and multiplication is tensor product. And using the same arguments as in the proof of main theorem, one can show that the nil radical of X, which is the nil radical of the endomorphism algebra. This is a finite dimensional local algebra, and its nil radical can be characterized, so it's a corollary. So if X is a non-negligible of moderate growth, and therefore rigid by the main theorem, then this radical is exactly the kernel of the trace map. And this means that quantum trace of every nilpotent endomorphism is zero, but trace of the identity is not zero. And that's exactly, so when you do semi-simplification of tensor categories, you want to get some abelian category, abelian semi-simple tensor category as a result. And the main abstraction to that is that traces of nilpotent endomorphisms don't have to vanish. And if they don't vanish, sometimes, then you will get, will not get an abelian semi-simple category, tensor category. But in this case, it turns out that you do, and so so we have a lemma that if C is a rigid, if C is rigid and quantum trace of nilpotent endomorphisms of each non-negligible object is zero, then this is true for all objects. And the corollary of this is that if C has moderate growth, braided moderate growth, then it admits a semi-simplification C bar, which is a semi-simple braided category of moderate growth, whose Grothendieck ring is this K of C. So this problem with the trace of nilpotent endomorphisms being non-zero never arises if you have moderate growth in braided categories. And therefore, using the theorem of Deligne in characteristic zero that was stated in the previous talk by Theo, and the results of Coulombier, Ostrich, and myself, who was also, I guess, mentioned in some form in the Verlinde case, but here, yes. So so we have a corollary that if C is a symmetric category, then semi-simplification C bar admits a fiber functor to supervector spaces in characteristic 0 and to the Verlinde category Ver P in characteristic P. So therefore, our category is equivalent to representation category of a linearly reductive affine group scheme in the category of supervector spaces or Verlinde P. And for supervector spaces, we know exactly what those are. They're just reductive groups and also OSP to N1 and products thereof of various sort, semi-direct, direct, and so on. And then for the Linde category, well, we have a conjecture of what those look like, but for k equal 2 and 3, it's a theorem. You also get linear reductive groups, which are classified by Nagata's theorem. And so this shows that this Z plus ring generated by non-negligible summons in tensor products of X and X dual of any symmetric tensor category of moderate growth is strongly constrained. The category doesn't need to be abelian, it just needs to be of moderate growth. So just take any category symmetric of moderate growth, Karubian, take an indecomposable object X, and look at non-negligible direct summons in tensor products X to the N times X star to the M, and we tensor them and we kill all the negligible summons. So that gives us a ring, and these rings are extremely constrained because they all have to come from groups of this sort. Okay, any questions up to this point? Okay, so let me now proceed to the proof. So let me, for the proof, I will assume for simplicity that I have a simple object, which of course is, if I have a semi-simple category, that's automatic because X was supposed to be indecomposable. And then we have morphisms, which are denoted by these arcs from X cross Y to 1, and from 1 to X cross Y, and from Y cross X to 1, and from 1 to Y cross X. So the first two exist because 1 is a direct summand in X tensor Y, and the other two are obtained from the first two by applying braiding. And then I'm going to normalize them so that the composition is the identity. I can do that because 1 is a direct summand in the tensor product. And now to establish rigidity, what we need, these are not quite the evaluation and co-evaluation maps. Because for those, we need that this, and this is somehow the crucial point, the main point, that this zigzag or snake is equal to 1. And here, it's not going to be equal to 1. In fact, if we do it in a fusion category, these snakes will be let's say we do it in a pivotal fusion category, spherical fusion category. These snakes are going to be reciprocal of the dimension of our object. So it's multiplication by 1 over d, where d is the dimension. Well, we know the dimension of simple objects is non-zero, so this is a nice number, and then we can renormalize to make it 1, and then the circles will evaluate to the dimension as usual. So that's for usual fusion categories. This is a different normalization. But here, we only have the normalization when the circles are equal to 1, and then the main worry is that these snakes might vanish. And that will mean that our rigidity is only weak rigidity. It's not a strong rigidity that we want. So we need to show that they don't vanish. So we need to show that these snakes are non-zero. Then we can renormalize to make them 1. So to do this, we define the inner product on endomorphisms of X to the N in the following way, that if I have two endomorphisms, X and Y, which are depicted in this picture, I compose them, and then I take their trace using the arcs from the above. So this trace is using my normalization. And then also if S is in the symmetric group, we can embed a symmetric group into the braid group as a set canonically by using braids with only upper crossings from left to right. And then we can define for every element of the symmetric group, we can define the corresponding braid Fs and the corresponding endomorphism of x to the n defined by this braid. So that will be called Fs. And then one can check, this is the main computation, that the inner product. So if so I assume the contrary, that one of those snakes vanishes. So that's the crucial point. I assume that they are zero. And then, or actually one of them is zero. And then it turns out that the inner product of Fs inverse with Ft, so the trace of their composition, is just delta St. So this matrix is diagonal, it's the identity matrix. So here is an example of how this happens, which represents kind of the general case is just a straightforward generalization of this computation. So suppose I want, I have the one permutation is the identity and the other is the switch of 1 and 2 in S2, so n equals 2. So then I have a picture like this for the trace. And then so my diagrammatics here is that I can do the usual things. I can move strands, but the only thing I cannot do is I cannot undo snakes because snake is in question. I cannot do the zigzag, undo the zigzags. But still I can move this strand here to the right to obtain this picture. And then I can undo the curl in the usual way that doesn't involve snakes. And then I get this thing which contains both the left and the right snake. And therefore, if one of them vanishes, then this thing will be zero. So this means that F1 inverse with Fs equals to 0. And this can be generalized to a higher number of strands. So this means, since this matrix is non-degenerate, this means that the dimension, that the Fs must be linearly independent in the space of endomorphisms of x to the n. So the dimension of x to the of endomorphism of x to the n, endomorphisms of x to the n, must be at least n factorial. And so this is a contradiction because we assumed moderate growth that for all n, this dimension, that there exists n for which this dimension is less than n factorial. And so that completes the proof. So you see the proof is not that hard. Of course, I missed some details, but it's not much longer than this. Any questions? Okay, so now let me pass to counterexamples. This means that I will explain why certain conditions cannot be removed. So first of all, we cannot remove the braided assumption. So in fact, in this proof, the braid relation, the third Rademeister move is crucial. I have not used it in this picture because I dealt with n equals 2, but once you get to n equals 3, you really must use it. And the counterexample showing that that assumption is essential is the following. It shows that this cannot be relaxed even to co-boundary categories, which is only maybe, well, it's like if you have a braided category, we're satisfying some mild conditions, it always has co-boundary structure, but not vice versa. So the co-boundary categories were described, well, I mean, they were basically essentially discussed by Drinfeld, co-boundary quasi-Hopf algebras, but then they were systematically studied by Henriques and Kamnitzer, and they showed that the category of crystals for a reductive group is a co-boundary category. Braided, so in a co-boundary category, the tensor power of an object carries the action not of the braid group, but of the so-called cactus group. And so the braided assumption cannot be relaxed even to a co-boundary. So the example is the category of crystals of linearized category of crystals of, let's say, simple group G, which is basically the limit when Q goes to 0 of the representation category of the quantum group GQ. So representation category of GQ is braided and therefore co-boundary by the Drinfeld construction, where you take braiding times the square of the braiding to the power minus 1/2, and it gives you a co-boundary structure. And when you take limit Q goes to 0, the braided structure gets destroyed, but co-boundary structure survives if you take the limit in the right way, which is not completely trivial. And to see that this is a counterexample, that this category is not rigid, it's enough to consider morphism from representation V lambda with highest weight lambda to V lambda double star. Well, this is unique up to scaling. And then we can define its Mugert squared norm, which is the trace of F. Well, it's not kind of Mugert squared norm. Trace of F times trace of F star inverse. And this is the quantum dimension of V lambda squared. And this goes to infinity as Q goes to 0. For example, if this V lambda is the two-dimensional representation of SL2, then this dimension Q of V lambda is Q plus Q inverse, and Q plus Q inverse squared goes to infinity when Q goes to 0. So this means that this category is not, the limiting category, whatever it is not rigid. In the case when the group is SL2, can be made especially explicit. This is so it can be made especially explicit. This is done in detail in the work of Alkadi and Stroinsky. And this is a so-called asymptotic temporally Lieb-Jones category. So we can consider the temporally Lieb-Jones category TLJ of delta, and take delta equals to minus Q inverse as usual. Then it corresponds to quantum SL2 with parameter Q. And then we can renormalize as above, so that the circle evaluates to 1, but the zigzag then will evaluate to delta inverse. With the usual category, the circle evaluates to delta, and the zigzag evaluates to 1. And now we can specialize to delta equal to infinity. And in that category, the circle still evaluates to 1, but the zigzag evaluates to 0. So home from M to N is spanned by the usual temporally Lieb-Jones diagram. When N inputs and M outputs, composition is concatenation and removing circles, but zigzag evaluates to 0. And this category, as I said, is discussed in great detail in this paper, recent paper. But these categories, so this is a counterexample showing that braided cannot be removed, but these categories have infinitely many simple objects. And it's an open question. We don't know whether if you impose that the category has finitely many simple objects, then and semi-simple, then it can be weakly rigid without being rigid. So this is not known. And there is a result to that extent, partial result to this extent, which is the following. So let's define growth dimension of an object Z as the limit when n goes to infinity of the length of Z to the n to the power of 1 over n. It can be shown that this limit exists. It's not difficult. And this follows from the fact that this number, length of Z to the n, let's call it Ln, it satisfies the inequality that Ln plus m is greater or equal to Ln times Lm. And any sequence satisfying this inequality, for this sequence, there is a limit in the moderate growth case, finite. And proposition is that if you have two simple objects, x and y, in a split semi-simple weakly rigid category C over K, which is not assumed to be braided anymore. And so if 1 is a direct summand in X tensor Y, and the gross dimension of X tensor Y is less than 4, then X is rigid and Y is X dual. And this bound is sharp, unfortunately. So if gross dimension equals 4, then there is a counterexample, namely take the two-dimensional object in the temporally Lieb-Jones category, asymptotic TLJ category corresponding to SL2. And so this, and both X and Y take that object V corresponding to the two-dimensional representation of SL2. So that would be a counterexample. This is not a rigid object. So this, as I said, so this is not a very interesting proposition. And the really interesting problem is whether weak rigidity without rigidity is possible for based fusion rings. If based fusion rings can admit categorifications that are weakly rigid without being rigid. And now another example showing that moderate growth cannot be dropped. And so counterexample is constructed in a similar way by renormalizing. So in this case, I will consider the oriented Brouwer category OB of T, which is the same as the Delign's category rep GLT, interpolated to complex T. So it's morphisms are basically, it's a diagrammatic category where morphisms are oriented Brouwer diagrams. And then we can renormalize it so that the circle is 1, but the wiggle is T inverse. And it's a symmetric category, by the way, so braided in particular. And now we can evaluate it at T equal infinity. And we get this asymptotic category OB infinity. And that's a symmetric category, which is weakly rigid, but was not rigid. And this showed that moderate growth cannot be dropped. And a similar example is an unoriented Brouwer category corresponding to interpolation of orthogonal groups. So this is rep OT in Delign's language. We can similarly degenerate it to category UB of infinity. And that's another example of such category of non-moderate growth, but braided, in which is only weakly rigid, but not rigid. Also, I should mention that if your category is not moderate growth, then nilpotent endomorphisms can have non-zero trace, even for symmetric categories. For example, we can consider this oriented Brouwer category OB of T in characteristic P, where T does not belong to FP. So in this case, we can simply take V to the P, where V is the standard object, and consider the map to V to the P, which is 1 minus the cyclic permutation. So we have 1 minus C to the power P is the same as 1 minus C to the P, which is 0. But trace of 1 is equal to T to the power P, and trace of C equals to T. So the condition, so the trace of 1 minus C is T to the P minus T, and that's not 0. So this category you cannot semi-simplify to get a semi-simple tensor category. And finally, I want to talk about applications to the work of Kazhdan and Lustig. So in early 90s, Kazhdan and Lustig proved that the category of admissible representations of a fine Lie algebra G hat for a simply laced simple complex Lie algebra G at level K, which is not a rational number less than dual Coxeter number, minus dual Coxeter number, which is not a rational number bigger than minus dual Coxeter number. is equivalent as a braided tensor category over the corresponding quantum of representations of the corresponding quantum group, GQ, where Q is the root of unity e to the pi I over k plus h check. And this is done in a series of 4 papers, and the fourth paper treats the most difficult and interesting case of rational Q, rational K, so K is less than minus h check. And in this case, these categories aren't semi-simple. And one of the most difficult points in this paper is proving that this category is rigid. So a priori, it's only known to be semi-rigid, which means an abelian R category with objects of finite length and simple unit. So let me explain how to deal with this and how to streamline that proof by using our results. So suppose C is a monoidal. Suppose C is an abelian monoidal category with right exact tensor product. And then I will say that C is 2 out of 3 rigid. If for and this is, by the way, also our results with David Penny's, which will be in the new version of this paper, but it is not there yet. It's not uploaded yet. So I'm going to call C 2 out of 3 rigid if for any short exact sequence 0 to x to y to z to 0, if 2 of the objects x, y, and z are rigid, then so is the third one. So a slight generalization of a result from the same paper of Kazhdan and Lustig is that every braided abelian R category is 2 out of 3 rigid. So that's a general property of such categories. And then I also need the notion of a category, or notion of recursive filtration. So suppose I have an Artinian monoidal category over a field K. Artinian means that finite dimensional Hom spaces and finite length. And let us denote by ER of C the set of isomorphism classes of irreducible objects. And then we say that, so what is a recursive filtration on this ERC? Recursive filtration relative to a subset S is an increasing exhaustive filtration of ERC by subsets ERN of C for n greater or equal to 0, such that for every n, and if you have an object X in ERN plus 1, then we can obtain it in the following way. We can find x1 through xm in our kind of generating set S, for which the composition series of the tensor product consists of a single copy of X, and the rest are elements of the previous set, ERN. So this means basically that X can be expressed in the Grothendieck ring as a polynomial on this xi, except that I don't expect, I don't assume at this point that the category has an exact tensor product. I only assume that it has right exact tensor product as in an R category, and so the notion of Grothendieck ring does not make sense, but this is the definition. And so the proposition that general proposition here that if C is a 2 out of 3 rigid category, which admits a recursive filtration relative to S, and if S consists of rigid objects, then C is rigid. So that's easy to prove. That's not has nothing to do with our theorem. This is just straightforward from these definitions. And then now this proposition together with the main theorem implies the following theorem, that if C is a braided semi-rigid category of moderate growth, which admits a recursive filtration with respect to a subset S consisting of non-negligible objects, then this category is rigid. So that's something that can be used in the Kazhdan-Lustig case. So in fact, so one can see that it has a recursive filtration with S being the set of fundamental representations. So representations are labeled by highest weights, and fundamental representations under some assumptions on the order of root of unities, it's not too small, will form a suitable set S, and also they will be non-negligible. And so this kind of streamlines their proof. So in fact, our theorem is not too necessary here. You can just, what I said streamlines that proof even without that theorem. But this can be used. The last remark I want to make is that Allen, Lentler, Schweigert, and Wood showed using the work of Huang, Liponsky, Zhang that representation category of reasonable vertex operator algebras are Grothendieck-Verdier categories. So they lack strong duality in general, and in particular, the dualizing object is the contragradient of V, which not necessarily is isomorphic to V, but they have this kind of partial duality structure. And sometimes they are not rigid, so you cannot prove that they are rigid. Sometimes tensor product is not exact, but the theorem, this last theorem gives us a really nice tool to prove rigidity of such categories in the cases when it does hold. In which case it will be an R category. And this has potential applications to logarithmic conformal field theory where such categories arise. Okay, thank you very much.